Okay, the next thing we're going to look at is Ferris wheels. Okay, so let's say that this is an interesting Ferris wheel. Okay, because it's this is the ground level. So apparently the construction people have dug out of the ground a half circle so the Ferris wheel can rotate above the ground and then back into the ground and then back to sea level. Okay, so here we have 0 degrees or 0 radians. And let's say the person is right here. Bam, okay? Now, one thing about this circle, there's a really famous kind of circle in math called the unit circle, okay? It gets used all the time. And the reason it's called the unit circle is the radius is 1 unit, okay? And I don't care what units you're using, inches, centimeters, light years, doesn't matter. So from here to here is 1, okay? I'm not going to put it in there because it's going to kind of crowd up the drawing, which is going to get sort of crowded anyway. But if I'm keeping track of the y-coordinate, for whatever reason, the y-coordinate of this person, do you agree? Like if I build a table here, bam, bam, let's say this is the angle, theta, I'll get to that in a second. Here's the y-coordinate. Just so you know, mathematicians use Greek letters all the time. This is the Greek letter theta, looks like a 0 with a little belt. And it is traditionally used for angle measurements, okay, if you're not used to seeing that. Anyway, look, we have one point that we can put in our chart here. Right at 0 degrees, or 0 radians, our y-coordinate of this person is just at 0, right? Great. Okay, now I'm just going to hit every factor of 30 and every factor of 45 to kind of chart out this person's progress, okay? So I'm going to see now what's the y-coordinate when I get to 30 degrees. That's also known as pi over 6, by the way. I know you're used to thinking in terms of 30 degrees, so I'll kind of use both right now. So where is the person now? Well, they're not down at the ground anymore. They're up a little bit. What is their y-coordinate right here? Well, for those of you that remember trig, there is a way to get that y-coordinate because we have a right angle here. So we can use SOHCAHTOA. We remember, hopefully, the radius, right? It's a unit circle, so the radius is a 1. So if this is a 1 and this is 30, can you get the opposite side? Yeah, right? SOHCAHTOA. Which one of those uses opposites and hypotenuses? Sine. So the sine of 30 degrees, that's going to equal my opposite. Let me call it the y-coordinate here, okay? The y-coordinate over the hypotenuse, 1. But this is kind of cute, because check it out. What's anything divided by a 1? Isn't that just itself? So we have sine of 30 degrees just actually equals that y-coordinate. Well, plug that into your calculator, and you'll get the sine of 30. It's a half, okay? So right at 30 degrees, I am at 1/2, all right? Actually, I'm going to go decimal on this just because I know what I'm going to do later. So let's call it 0.5, okay? Great. So let's go now to 45 degrees as we journey up to the highest heights here. So 45 degrees is right in between 0 and 90. Bam. So now we're at 45 degrees. How can I figure out what y is now? Well, just same thing, right? It's opposite over the hypotenuse. This is a 1. So it looks to me like, oh, what's going to change in this thing? Isn't it just I'm dealing with the sine of 45 now? And that's going to be my y-coordinate? So if you put that into your calculator, go ahead and pause the video if you want. It's kind of a famous value, so I just happen to remember it. At 45, we are now sky high, 0.707 up in the air. Okay, that's what that y-coordinate is. And here you might start seeing like, oh, I kind of get the pattern now. The next factor of 30 is 60. So where are we at 60 degrees? Well, our triangle, I should probably erase this, shouldn't I? Our triangle now will be at 60, bam, bam. 60 degrees is pi over 3 radians. So at pi over 3 radians, what's my y coordinate? Well, it's just going to be sine of 60 now, right? We'll equal that. Again, kind of a famous value. I happen to know it. It's 0.866. 0.866. And then, when we finally get up to the maximal height, when we're right up here, well, guess what? What's my y coordinate now? Well, don't forget the radius of the circle. It's 1, right? We're a unit circle. So, at 90 degrees, I'm at 1. Okay? Now, you can use symmetry on the backside of this Ferris wheel journey. I'm running out of room on this table, darn it. But the next factor of 30 is 120. Can you guess if I go to 120, so that I would be, bam, double the 160, right? But can you tell, if I had drawn these triangles at even remotely, they're not too bad. Can you tell that the two triangles I drew it perfectly will be at the same height level? Or just trust me on that? So guess what? Guess what the person's y coordinate is now? Well, it's just the same as a 60. 0.866. 0.866. And then when we go to the next 45, that's 135, okay? If I add 45 to 90. And can you tell when I do that, let's see if I can salvage all this thing here. When I go to 135, that'll be all the way to 90 and then another 45 degrees. Okay, that's 135. But can you tell it's just going to be the same height as at 45? Oops, sorry, I ran out of camera. Can you tell that this height will be the same height as the 45 there? So at 135, I'll be at 0.707. And now you can probably see, oh, well, when I go to my next 30 degrees, 150, I'll be at 0.5, and then at 180, I'm back here so that I am now at ground level again, right? 0. And then an interesting thing happens, because if I go to my next 30 degrees, 210, can you tell I will now be in the ground, right? Here's 180. Yep, so let me get rid of these things. So here is 180, and you got to go another 30 degrees, Now we're down here. So can you tell my y coordinate is now negative? And if you are seeing how symmetrical this circle is, you might be able to tell if this is 30 degrees right here. Guess what this angle is? You vertical angles experts. This is 30 degrees. So however high we were up here, we're going to be down in the ground that much, right? Because the triangles are exactly the same size. So instead of positive 0.5, we'll be at negative 0.5 right here, okay? If I go to my next 45 degree angle, it's 225, and at 225, it'll be right there, which will be the same height as the 45 degree one, except negative. So I'll be at negative 0.707, and I'm running on a chart here, and I'm just gonna stop, because you can probably see what's going on. Okay. I don't know if you noticed how we got all these values, but we were just taking the sine of the angle, right? To get this 0.866, we just took the sine of 60. To get this 90, well, we didn't actually do it, but try it on your calculator. What's the sine of 90? It's going to be 1, okay? All of these are the sine of the angle. So in general, so I got off camera there, sorry. In general, if you have some random theta here, this chart here is just showing you the sine of that theta. So I got to show you something kind of amazing, because you've actually just figured out a function. You figured out what the sine of theta function, or not what it looks like yet, but at least what its y values are. But the next thing is like, holy cow, don't you want to graph this and see what it looks like? We're used to graphing parabolas or lines. Some of you might know exponential functions, square roots. I don't know if you've seen a trig function, like the sine of theta graphed, but it's one of the most famous curves in all of mathematics. It gets used all the time. Oh my goodness gracious. Electromagnetic waves, like any kind of wave, goes by sine waves. Tidal cycles, they go up and they go down. Oh, wait, I shouldn't give it away. that's what it's going to do. Here, I'm going to make a set of axes here, but since I don't care about negative theta, I'm just going to draw the positive theta, okay? And then let's just graph this. So 0, 0, bam. Oh, and I should probably put in, okay, so let's do, here, this will be 180, this will be 360. That means this is 90, right? Ish. 45 is right here. Here's 30, and here's 60. Obviously, I'm not doing this very well. 90, what is it? 120, 135, 150, okay, etc. I don't know if you can see that little. Anyway, let's graph these things. I want to see what this looks like. So 0, 0, got it. 30 and up 0.5. Okay, so let's just say this is 1. Let's say this is negative 1. So 30.5, bam. 40 and 0.707-ish, right there, right? 0.8664, 60 degrees. I'm getting up close to 1 here. Oh, and actually, I just know what the curve should look like, so I'm just kind of modifying this a little bit here. And then at 90 degrees, I'm at 1, right? 90 at 1. So bam. And then it starts to go down because we're past the peak of the Ferris wheel. So now we're going to start going down. So I have 120, I'm back at 0.866. Bam, 135 right here. Oh, jeepers creepers. 135 right in here. Really should, I need some graph paper. 150, I'm back at 1.5, and then like this, okay? And then, I don't know if you can tell what's going to happen, but it's going to be the exact same values, except that they'll be negative. So this curve here that I've started to develop is just going to go negative now. And where's it going to bottom out? It's going to bottom out at 270, because then your y value is negative 1. So if I fit 260 in here, 260 is right in between these. I'm sorry, I'm saying 260, 270. If I put 270 in here, I'll be at negative 1. So that can kind of guide me into, man, this is like not the same at all, whatever. Look, I just got to fix this a little bit, kids. Bam, bam. Here's 360. Here's 270. 270 and negative 1. So I should have like that. Ugh. It's actually so much more beautiful when you do it on graph paper, right? It's a really pretty curve that just goes like this and like this and like this and like this. Okay, because you can probably tell you can just keep going around the Ferris wheel, right? So yeah, this is a sine wave. It gets used all over the place, all over the place. So it's really important to know it. I just want to draw a couple of things to your attention. Where does the sine wave start? It starts right at 0, doesn't it? It doesn't start up here, it doesn't start down here, it starts right at the origin. So one thing for you to remember is sine starts at 0, 0. And then, yeah, it has the symmetry to it, and I think you're good. What do you need to know here? I need you to memorize really just the first coordinate, the first quadrant is fine, okay? If you can have those memorized, that would be good. Except that we don't usually use the decimal versions because the decimal versions are an approximation. So let me lay it on you here. What the, well, 0.5 you know is 1/2, right? They usually use fractions, so I want you to know the fractions. 0.707, you can get it using the Pythagorean theorem, but I don't have time to show that to you. This 0.707 ends up being 1 over root 2. Okay, can you see that? 1 over root 2. And then this 60 degrees, that 0.866, that's an approximation for square root 3 over 2. And those might seem random to you, but I swear you can find them using the Pythagorean theorem. Like I said, I just don't have time. It's already a 14-minute video. Okay, the other thing that I want you to know is that really, yeah, this is the y-coordinate, and that's great. But really, aren't all these values just the sine of this angle, the sine of this angle, the sine of this angle, the sine of this angle? So I want you to really think of this more as, here's the sine of theta, okay? You can put this in your charts if you want to. You can go all the way down. I only have the first quadrant here, but you can go all the way down if you just remember that symmetry. This is what I need memorized. So that if I say, hey, what's the sine of 45 degrees? You need to know right away, oh, that's just 1 over square root of 2, okay? And like, what's the sine of 0? 0. What's the sine of 90? 1. So just have those memorized and on autopilot so that you don't get slowed up. It's just like learning the times tables. Okay?